Eurostat makes its statistical data available through a public REST API at no cost. You can query population figures, GDP, greenhouse gas emissions, trade balances, all of it. The catch is the format. Eurostat uses JsonStat version 2.0, a compact representation of multidimensional data cubes that looks almost nothing like the JSON you are used to reading. A response for population data with dimensions of country, year, and sex does not give you an array of objects with country and year and sex fields. It gives you a flat array of numbers, a separate dictionary mapping dimension codes to positions, and a size array telling you how many values each dimension has. To get from that response to a typed Kotlin data class, you need a parser that understands the JsonStat addressing scheme. In this episode, we built that parser from scratch, explain the algorithm in detail, and show how PopulationCellMapper adapts the flat output into real domain objects. Open the Eurostat API in a browser and request the population dataset demo.pgen with a filter for total sex and a handful of countries. The response is a JSON object with 5 mandatory fields. The ID field is an array of dimension names, for example geo, time, sex. The size field is a parallel array of integers giving the count of categories in each dimension. 27 countries, 24 years, 3 sex values. The dimension field is a nested object that maps each dimension name to its category metadata, a map from category code to its integer index position, and optionally a label map with human-readable names. The value field is either a JSON object with stringified integer keys or a plain JSON array. The data lives in value. Everything else tells you how to decode it. This structure is extremely compact. A 27 by 24 by 3 cube fits in a single response with no repeated keys. The first step is deserializing the raw JSON into Kotlin data classes. JsonStatResponse in core JsonStat mirrors the API shape exactly. The id field becomes a list of strings. The size field becomes a list of integers. The dimension field becomes a list of integers. The dimension field becomes a lib from string to JsonStatDimension. The dimension object holds an optional label string and the required category. The category holds two things: index, which is a map from category code to its integer position, and label, which is an optional map from category code to its human-readable name. The value field is declared as JsonElement, the raw Kotlin.serialization type for any JSON value, because its shape is dynamic the .serialization type for any JSON value, because its shape is dynamic. If the response is sparse, value is a JSON object with stringing-fact effect. If dense, it is a plain JSON array. Trying to deserialize value directly into a typed Kotlin structure would require a custom deserializer. Keeping it as JsonElement lets the parser handle both cases with a simple when expression. The goal of the parser is not to expose the raw JSON-stat structure to callers. Feature modules should not have to understand dimension indices and size arrays. The output is a flat list of JsonStatCell objects, one per observation. Each cell carries 3 fields. The dimensions field is a map from dimension name to category code, for example geo mapped to PL, time mapped to 23, sex mapped to F. The dimension labels field is a parallel map with the human-readable version, geo mapped to Poland, time mapped to 23.3, sex mapped to female. The value field is a nullable double. It is null when the JsonStat response has no observation for that position, which happens in sparse datasets. With this design, a feature module receives a flat list of typed cells and can filter, group, and map them without knowing anything about the JsonStat addressing scheme. The parser is a one-time implementation that every feature module consumes. The core challenge is converting a flat integer index into a set of per-dimension positions. This is the same problem as converting a flat memory address into row and column coordinates in a multidimensional array. The algorithm uses a stride table called multipliers in the code. For a three-dimension dataset with sizes 27, 24, 3, the multipliers are computed right to left. The last multiplier is always 1. The innermost dimension increments by 1 per step. The second multiplier is 1 times 3, which is 3. The first multiplier is 3 times 24, which is 72. To decode flat index 100, divide by 72. Take modulo 27, get 1, that is dimension 0, position 1, which maps to country index 1. Divide by 3, take modulo 24, get 9, that is dimension 1, position 9, which maps to year index 9. Divide by 1, take modulo 3, get 1 sex index 1, 3 divisions, 3 modulos, complete decoding in constant time per dimension. Here is the implementation in full. The computeMultipliers function works the size array right to left, or accumulating a running product. The loop starts at the last dimension and works backwards. At each step, the current accumulated product becomes the multiplier for that dimension, then the product is multiplied by the size at that position. The result is an int array where entry 0 holds the stride for the outermost dimension and the last entry is always 1. Notice the overflow check. The product is tracked as a long and validated before casting to int. For Eurostat datasets, this overflow never occurs in practice, but the guard is there because JsonStat in principle allows any size. This 6-line function is the foundation of the entire parcel. Every subsequent lookup in BuildCell calls into this multiplier array. The complexity is linear in the number of dimensions, which for Eurostat is always 2 to 4. Before iterating over values, the parser builds 2 lookup tables per dimension. The first is the reversed category index. The category.index field in JSON-stat maps from category code to its integer position. For example, PL maps to 0, DE maps to 1. The parser inverts this into an array of strings, where position 0 holds PL and position 1 holds DE. This inversion is done once and stored in a map from dimension name to a string array. The build label lookups function creates this reversed map. The second lookup table maps category code to human readable label. This is the category label map from the JsonStatResponse, which is optional. If absent, the parser falls back to the code itself. Both tables are built once before the main value loop, making each per cell lookup and all of one array access or map get. For a dataset with 10,000 values and 4 dimensions, the total cost of the lookup table construction is negligible. The value field in a JsonStatResponse can be either a JSON object or a JSON array. When it is a JSON object, the keys are stringified integer indices and the values are the observations. This is the sparse format. Positions with no observation are simply absent from the object. The parser handles this with the JsonObject branch. It iterates over the entries, passes each key as an integer, and calls BuildCell with that flat index. Null is returned for any entry whose key is not a valid integer, which should not happen in a well-formed response but is guarded against with map_null. When the value field is a JSON array, every position is present in order. This is the dense format. The parser handles this with the JsonArray branch using map_indexed, where the index is the flat position directly. Both branches produce a list of JsonStatCell and the caller sees no difference. The when expression on the raw JSON element makes the dispatch clean and exhaustive. The parser produces a flat list of JsonStatCell objects, that is the boundary between core JsonStat and the feature modules. PopulationCellMapper in feature population takes that list and converts it into domain types. The map function filters cells to those where the age dimension equals dateAll, groups them by country and year key, and separates the sex equals T, M, and F values into total male and female fields. The map to snapshots function handles the demographic pyramid. It processes cells where age matches one of the 18 5-year cohort codes, building a population cohort for each cohort and a populations cohort for each country-year combination. Notice that the mapper never reads JsonStatResponse. It works only on the flat cell list. The cell's dimension labels map provides a human-readable country name without the mapper needing to know how labels are structured in the raw response. This separation means the mapper is easy to unit test independently of the HTTP layer. JsonStat represents the absence of an observation as JSON null in the dense array form, or simply by omitting the index key in the sparse object form. The parser preserves null values as value equals null in the JsonStatCell. This is an intentional design choice. Silently dropping null cells would hide gaps in the data. Features that build charts need to decide whether a null means 0, means a gap in a line chart, or means the data point should be excluded from an average. The parser cannot make that decision. It does not know what the data represents. So it passes null through, and the mapper decides. In PopulationCellMapper, null values are skipped with a continue statement. A null population count has no meaningful representation in a bar chart. In a line chart of temperature anomalies, null might render as a gap. The null preservation contract ensures that decision stays with the domain, where it belongs. The JsonStat parser has a suite of unit tests in core JsonStat commonTest. Tests cover both sparse and dense value formats, null preservation, label resolution, dimension index inversion, and the multiplier computation in isolation. The computeMultipliers function is marked internal specific key so it can be called directly from tests, verifying the stride table without having to construct a full JsonStat response. Running the full test suite with the Gradle command core JsonStat all tests takes about 1 second on JVM. The tests use synthetic fixtures, small JsonStat responses with 2 or 3 dimensions and a handful of values, not real API responses. This keeps the tests fast and deterministic. Real API responses are large and can change when Eurostat updates its datasets. The contract being tested is the algorithm, not the specific data, so synthetic fixtures are the right choice. The parcel is fully exercised before it ever touches the network. JsonStat is an unusual format, but the algorithm to decode it is straightforward once you see it clearly. Compute a multiplier for each dimension by walking the size array right to left. For each flat index, divide by the multiplier and take the modulo of the dimension size. Look up the resulting position in the inverted category index. The entire parcel is about 130 lines in the codebase, most of which is error handling, kdoc, and the 2 auxiliary lookup functions. The key insight is that the parcel is generic. It knows nothing about population, GDP, or greenhouse gases. It produces JsonCell objects with string maps. Every feature module then writes its own mapper function that interprets those strings according to its domain model. This separation, generic parcel, domain-specific mapper, is what makes it possible to add new Eurostat datasets by writing only a mapper, not a parcel. Clone the repo, open JsonStatParser.txt, and the algorithm is right there. Subscribe for more on Android AI tooling and Kotlin Multiplatform.